Hello and welcome to CircuitShepherd. In this video, we'll investigate how to design inverting operational amplifier circuits with CircuitShepherd. We'll show how to define and synthesize a completely arbitrary inverting linear transfer function, including a DC offset, and also provide the AC gain with a well-defined bandwidth limit. Additionally, the different measurement modes of the meters are discussed. Let's start with the most simple version of the inverting operational amplifier circuit and plot the DC transfer function. While the negative voltage gain is defined by the proportion of R1 to R2, we can add a voltage source to the positive input of the operational amplifier to add an offset to the DC transfer function. To inspect the AC transfer characteristics, we can copy the DC sweep plot and switch to Bode plot mode. Note that the maximum bandwidth of the circuit is limited by the gain bandwidth product of the operational amplifier. That the gain curve becomes flat again for high frequencies is owed to the fact that in CircuitShepherd operational amplifiers are modeled with a specific output resistance. A professional design will always ensure a well-defined bandwidth limit, just high enough as needed, which can be achieved by adding a capacitor in parallel to R1. After gaining an intuitive understanding of the circuit, we want to set up measurements which clearly define the transfer characteristics in both the DC and AC domain. There are multiple ways of achieving this, so let's take a closer look at the voltmeter modes to explore the possibilities we have. By default, the voltmeter is in operating point mode, which simply measures the DC voltage of the circuit shown. Of course, the measured voltage will change if either V1 or V2 is changed. Let's copy as alias to adopt the wiring of the original voltmeter, but set up a different measurement mode. Very similar to the operating point mode is the DC sweep mode. The only difference is that the value of a specified sweep source is overridden by the sweep value just for this one measurement. Both voltage and current sources can be swept for this purpose. Since we implicitly sweep V1 to 4 volts for the measurement, the measured value stays the same even if we change the operating point of V1. Of course, changes in V2 will still lead to a different result. Now there are two more modes based on DC analysis. Let's try out the LF mode first. So the LF stands for low frequency. In this mode, the meter measures the small signal gain for slow changes of the input. In this sense, slow means that for the measurement, all inductors in the circuits are implicitly replaced by virtual short circuits and all capacitors are replaced by open circuits. So the LF meter measures the gradient of the DC transfer function at the actual operating point. For linear circuits, this value is, of course, not influenced by changes of any constant voltage or current source. The HF, or high-frequency mode, measures the small signal gain for fast changes. In this sense, fast means that for the measurement, all capacitors in the circuit are implicitly replaced by virtual short circuits, and all inductors are replaced by open circuits. In our case, the shorted capacitor leads to a voltage gain of approximately 0. Note that HF and LF mode always lead to the exact same result if neither capacitors nor inductors are used in the circuit. The AC mode simply measures a point in the Bode plot. Interestingly, in this particular circuit, the AC gain for low frequencies equals the LF measurement. But note that this does not need to be necessarily the case in general. It always depends on the particular circuit if the LF or HF measurements, which are only based on pure DC analysis, also correspond to certain points in the Bode plot. In this regard, it's important to know that CircuitShepherd always considers semiconductors to have infinite bandwidth for HF measurements. Now, let's dive into the exciting part, setting up auto parts and design targets. This will allow CircuitShepherd's parameter optimization algorithm to determine the optimal part values for us. For instance, we can set two DC sweep points as design targets to clearly define the DC transfer curve. And given that the bode plot displays an unambiguous phase curve, we can employ a phase design target to establish a bandwidth limit. While our design targets are now clearly defined, it's worth exploring some alternatives. For instance, rather than opting for a second DC sweep point, we could establish an AC gain for low frequencies. Additionally, to prevent interference with bandwidth limit modifications, we might consider using the small signal gain for low frequencies as a design target instead of the AC gain. Remember, there are numerous ways to configure a circuit, and some methods offer greater flexibility in adapting to target value changes than others. For the final design, we synthesize the reference voltage at the negative input of the operational amplifier using a voltage divider. If needed, a proper bias current compensation can be ensured by setting up a little entangled helper circuit to match the inner resistances of the voltage dividers. Before we finish, it should be mentioned that the short circuits caused by inductors and capacitors in LF and HF mode are just virtualized by very high conductivities. These can be adjusted on the second parameter page of the part. Stay tuned for more in the next videos. Thanks for watching. See you later.